Hi students, in today's session we are going to discuss the next synthesis technique for nanostructures. The synthesis technique that we are going to learn today is evaporation, a quite simple technique. So, evaporation or evaporative deposition of thin films is a process by which the material to be deposited is heated to a high vapor pressure in vacuum. That is, uh, the material to be deposited is taken and it is heated to a high temperature. Then the material begins to vaporize and the vapor is allowed to condense on the substrate and thus the thin film deposition is attained. The heating of the material to be evaporated is done either electrically by resistive heating or by electron bombardment. So, how can the heating of the material be done? So, these are one is by resistive heating, that is Joule's heating, and by electron bombardment. Now, if the material to be deposited is heated by means of resistive heating, then the synthesis technique is called thermal evaporation. And if the material to be deposited is evaporated by means of electron bombardment, then the method is called electron beam evaporation. So I hope this is clear to you. That is, here the thin films are formed when the material to be deposited is heated and the material gets vaporized. The vapor atoms then condense on the surface, that is the substrate, and the thin film is grown there. Now, heating of the material to be deposited can be done either by resistive heating or by electron bombardment. If it is done by resistive heating, then the method is called thermal evaporation, and if it is by electron bombardment, then electron beam evaporation. So, first let us go to thermal evaporation. Here, a filament carrying high current from 10 to 100 ampere is used to vaporize the material to be deposited. The range of temperature depends on the nature of the filament and the material to be vaporized. Now, the current passes through the filament to produce sufficient heat, and this heat is used to vaporize the material to be deposited. Now, the vaporized material then travels through the chamber and gets deposited on the substrate, which is to be coated. I hope you have understood. Now, this entire process takes place in a vacuum chamber. Higher the vacuum or better the vacuum, the more efficiently the material will be deposited on the substrate. If it is not carried out in a vacuum environment, then what is the difference? If it's not carried out in a vacuum chamber, there will be some kind of gas inside the chamber. That is either air or some other gases, unwanted gases will be present inside the chamber, and these vaporized atoms will collide with these air molecules, and effective deposition of vapor atoms on the substrate will not take place. So, if the vacuum is better or higher the vacuum, there will be less number of unwanted molecules in the chamber. That is, less number of, we are meaning air molecules in the chamber. So, the mean free path is increased. Mean free path of the vapor atoms is increased. That is, when the material gets vaporized, it forms vapor atoms, and the vapor what is mean free path? It is the distance between two successive collisions. So, the vapor atom can travel a very long distance without colliding with any other unwanted molecules. And it can reach the substrate and get condensed and deposited on it. Okay, so the entire process is carried out in a vacuum chamber. Now, the rate of deposition is controlled by the current passing through the filament. Now, here I have given the figure of a thermal evaporation system. Now, the All the diagrams or the figures that I've used in this video session have been scanned from the textbook Introduction to Nanoscience and Nanotechnology by K.K. Chadobadhyaya and A.N. Banerjee, which is your book of study. So here you can see this is the filament, and this is a vacuum chamber. It's connected to a vacuum pump to maintain the vacuum inside. Now this is our substrate where the film has to be deposited, and this forms the target material. Now when the current passes through the filament, it gets heated. The target material in turn gets vaporized, and the vapor atoms move towards the substrate, gets condensed on it, and the thin film is grown on the surface of the substrate. So I hope thermal evaporation technique is clear. Now in the thermal evaporation process, we use what are called evaporation sources. Evaporation sources are either in the form of metal boats or crucibles, inside which the material to be evaporated is taken. So such metal boats or crucibles are used in the thermal evaporation technique. So what is this metal boat or what are these crucibles? They are called evaporation sources. These include first the metal boat. So metal boat is made of refractory materials like tungsten, molybdenum, etc. So refractory materials means materials can withstand a large amount of heat. So inside these evaporation sources, you keep the material to be deposited is kept. Okay. And the other kind of evaporation sources are heat shielded crucible made of alumina or ceramic materials. Again, materials which can withstand a large amount of heat. Now the metal boat with the material to be evaporated is heated again by passing the high current, and the amount of heat produced here is I square R. As a result, the material gets vaporized, it moves towards the substrate, gets condensed and deposited on the substrate. Now, if the source material has the possibility of alloying with the boat material, that is at high temperature, if the source material that we are using to form the thin film has a possibility of forming an alloy with the boat material, then the boat cannot be used. Metal boats cannot be used as evaporation sources here. Then what is done is a ceramic coated boats or ceramic crucible may be used. Inside the ceramic crucible, you keep the material to be deposited, and the ceramic crucible is heated inside a heating coil, and the crucible along with the source material is heated up when current is passed through the coil. So that is shown in the figure here. Yeah, this is the crucible, ceramic crucible, and this is the heating coil, and the material to be heated is placed inside the crucible. Now the crucible and the material to be deposited is gets heated when current passes through the coil, and the deposition material gets vaporized, it condenses and gets deposited on the substrate. So this much about thermal evaporation technique. Next, we go to electron beam evaporation. Here, the heat required to vaporize the material to be deposited is obtained from high energy electron beams. The electron beam is produced by an electron gun which uses the thermionic emission of electrons from a heated cathode. That is, there will be a heated cathode and it will emit electrons by thermionic emission. So that forms the electron gun or the source of electrons. Now the emitted electrons, it's not electrodes, sorry, it's electrons. The emitted electrons are accelerated towards the anode by the high potential difference. Now the electrons are of negative charge and automatically they will be attracted towards the positive electrode, that is the anode. Now what is the anode here? The material to be deposited or The crucible containing the material to be deposited can act as the anode, so that the electron beam will come and fall on the material to be deposited or the crucible containing the material, and it will transfer its energy to this material. It gets heated, vaporized and deposited on the substrate. Here, a magnetic field is used to bend the electron beam so that it falls on the source material. That is, the electron source or the electron gun is not placed in line with the material to be evaporated, or it's not placed just the gun is placed below the evaporation line. Now, the evaporation of the energetic electron beam raises the temperature, source material begins to get evaporated. Now, since the electron beams are highly localized to a very small area, it is possible to obtain a much localized heating of the material to be evaporated with high density of evaporation power. I'll show you the figure of an electron beam evaporation unit. This is also, the figure is taken from the same text, Introduction to Nanoscience and Nanotechnology by K.K. Chadobadhyaya and A.N. Banerjee, a book of study. Now here you see the electron gun, that is a heated cathode from which electrons are emitted by thermionic emission, and here by means of a magnetic field or a deflecting magnet, the path of the electrons are curved and it is allowed to reach the source, that is the material to be deposited. And since they are highly focused, it can be used to heat a very small area of the source, and the source atoms get vaporized, they fall on the substrate and you get the thin film. Now the third technique that we are going to learn here is chemical vapor deposition. So this is a very common technique used for nanomaterial synthesis. In this technique, the thin films are synthesized by means of a chemical reaction between the components in vapor phase to form a solid film at the substrate. So, in this method, there is a substrate and the thin film is coated on the substrate by means of the chemical reaction between some components in the vapor phase. Micro and nano fabrications widely uses CVD method to deposit materials in monocrystalline, polycrystalline, amorphous and epitaxial forms. The materials formed using chemical vapor deposition include silicon, carbon fiber, carbon nanofiber, nanofilaments, nanotubes, nanorods, then silicon dioxide, silicon germanium, silicon carbide nanostructures, etc. Now, the steps involved in the chemical vapor deposition process include: first, transport of the reactants via forced and free convection and diffusion. By these means, the reactants enter into the chamber where the chemical vapor deposition take place. Then, the reactants are adsorbed on the surface of the substrate. The reactants adsorb on the surface of the substrate, that is, growth reactions like pyrolysis, oxidation, hydrolysis, reduction, displacement, etc. All these reactions occur either in the gaseous phase, as these reactants are transported into the chamber before they reach the substrate. Either in the gaseous phase these reactions will take place, or these reactions can take place on the adsorbed surface, resulting in the growth of the required material on the substrate. Now, as a result of this reaction, in addition to the material required to form the thin film, many other byproducts will also be formed, which have to be desorbed from the substrate surface. So, the next step is desorption of byproducts from the surface. Then, these desorbed byproducts are transported or diffused away from the substrate. Now, the final step is incorporation of these condensed solid products into the nanostructure for growing the film. Okay, we incorporate all these solid products to form the film. So, these are the 5 steps involved. I'll repeat once again. The first step is transportation of the reactants via into the chemical vapor deposition chamber by means of forced and free convection and by diffusion. Then the second step is adsorption of reactants on the surface. Now, for the growth mechanism to take place, either chemical reactions like pyrolysis, oxidation, hydrolysis, reduction, displacement, etc., will occur in the gaseous phase of the reactants itself, or the reactants will adsorb onto the surface of the substrate and the chemical reaction will take place. അതായത് ആദ്യം റിയാക്റ്റൻസിനെ ചേംബറിൻ്റെ ഉള്ളിലേക്ക് ട്രാൻസ്പോർട്ട് ചെയ്യുന്നു, പിന്നെ റിയാക്റ്റൻസ് സബ്സ്ട്രേറ്റ് സർഫസിൽ അഡ്സോർബ് ചെയ്യുന്നു. അഡ്സോർബ് ചെയ്യുന്നതിന് മുന്നെയോ അല്ലെങ്കിൽ അഡ്സോർബ് ചെയ്തതിന് ശേഷമോ ഇത്തരം കെമിക്കൽ റിയാക്ഷൻസ് നടന്ന് എന്ത് മെറ്റീരിയലിൻ്റെ ആണോ ഫിലിം ഉണ്ടാക്കേണ്ടത് ആ മെറ്റീരിയൽ can be synthesized. That is, after these chemical reactions, either in the gaseous phase or on the adsorbed surface, the material to be grown or the material whose thin film is to be synthesized is formed on the surface. Now, as a result of the chemical reaction, several byproducts will also be formed which are not required on the surface and they have to be desorbed. That is the third step. Next, these desorbed byproducts have to be transported or diffused from the surface. And the final step is the incorporation of the condensed solid products to form the thin film. Okay, so in this session, we have discussed about the evaporative deposition technique, which involves resistive heating technique and electron beam evaporation technique. And we have learned a next technique, that is chemical vapor deposition technique, where the reactant molecules in the gaseous phase undergo a chemical reaction to form the solid materials which will incorporate themselves to form the thin film on the substrate. I hope this session is clear to all of you. If you have any doubts, please do contact. Thank you.